So think about it this way. Every material has a secret identity. It's this whole set of properties that only really shows up under certain conditions. And heat is the key that unlocks that identity.
I mean, we all know these changes happen, right? A polymer gets soft, a crystal might lose some water, a compound might completely break down. But for scientists and engineers, the real trick is knowing exactly when and how these transformations go down. So, how do you watch these secrets unfold in real time?
And that, my friends, brings us to our main investigative technique. We are about to conduct a heat interrogation. We're going to use this incredible tool that's designed to make materials spill all their secrets.
And that technique is called Differential Thermal Analysis, or just DTA for short. Now, the idea behind it is actually brilliantly simple. You take your material, that's the sample, and you heat it up right next to a reference material, one that we know for a fact won't react to the heat. By comparing the two as things get hotter, the sample's secrets just have nowhere left to hide.
Okay, picture this like a police lineup. On one side, you've got your suspect. That's the sample we're investigating. And on the other side, you've got the control, a really stable reference material that we know won't do anything funny when the heat is on. This control gives us the perfect unchanging baseline to measure everything against. Now, the process itself is super precise. You put both the suspect and the control into a furnace, and you heat them up at the exact same constant rate. Then you've got these incredibly sensitive sensors that measure any tiny temperature difference that pops up between them. And that difference, which we call delta T, is the crucial piece of evidence we've been looking for. So that temperature difference, it isn't just a random number, it is the evidence. And when we plot it out against the rising furnace temperature, we get something totally unique, something we like to call the material's thermal fingerprint. The result is this graph, the DTA curve. You can think of it as the final interrogation report. Any little wiggle or bump that deviates from that perfectly flat baseline means something important is happening inside our sample. Every single peak and every valley in this fingerprint tells us about a specific event. Okay, let's break down the first type of clue. Let's say our sample suddenly needs to absorb a bunch of energy to change, like to melt or for water to evaporate out of its structure. When that happens, it'll actually get momentarily colder than the reference. It's sucking in energy from its surroundings, and on our curve, that shows up as a big downward peak. We call that an endothermic reaction. But, of course, the opposite can happen too. Sometimes a change, like crystallization or maybe oxidation, will cause the sample to release a sudden burst of energy. When that happens, our sample briefly becomes hotter than the reference, and that release of heat creates a sharp upward peak on our graph, signaling an exothermic reaction.
And honestly, that's the real magic of this whole technique. You're not just staring at a graph, you are literally reading a story. A downward peak might be the chapter about the material melting. An upward peak could be the part of the story where it crystallizes into a totally new form.
So, talk is cheap, right? Let's open up a real-world case file. We're going to put a compound called calcium oxalate monohydrate under the heat lamp and see exactly what secrets it's willing to give up.
All right, check this out. As we start heating this stuff up, three big things happen. First, right around 200 degrees Celsius, boom, we see a downward endothermic peak. That's the material kicking out its water molecule. It's called dehydration. Then things stay quiet for a while, until we hit about 450 degrees, and bam, a sharp upward exothermic peak. At this point, it's oxidizing and turning into calcium carbonate. Then finally, way up at 840 degrees, we get one last downward peak as it decomposes for the final time into calcium oxide. So, in the end, the DTA curve didn't just tell us that the material changed. It gave us a precise step-by-step story of how it changed and at exactly what temperatures. It's the material's completely unforgeable thermal fingerprint.
And look, this isn't just some neat lab trick. This whole interrogation technique is absolutely crucial in so many industries, solving real-world problems every single day.
Seriously, this technique is everywhere. In the pharmaceutical world, it makes sure a new drug isn't going to break down on the shelf. In the food industry, it helps perfect the melting point of your favorite chocolate bar. Geologists use it to figure out what minerals are in a rock sample, and engineers rely on it for quality control on, well, everything from plastics to jet engine parts.